Hello dear learners, I welcome you all to the third module, that is Introduction to Magnetism of the SWAYAM MOOC on Electricity and Electrical Wiring. I am Dr. Smritimala Sharma, Assistant Professor in Physics, B. Borua College, Guwahati. Module 3 has been divided into 3 units. In the first unit, we will discuss magnetic property of materials. Here we will focus on what is a magnet, properties of classification, what is magnetism, origin of magnetism, basic parameters for magnetic materials, types of magnetic materials, and applications. What is a magnet? A magnet is any object that produces its own magnetic field that interacts with other magnetic fields. Magnets have two poles, a north pole and a south pole. The magnetic field is represented by field lines that start at a magnet's north pole and end at the south pole. This magnetic field is invisible. However, it is mainly responsible for the most of the notable properties of magnet. According to these magnetic properties, a magnet possesses a force that pulls on other ferromagnetic materials such as iron and attracts or repels other magnets. A magnet shows north and south direction when suspended freely. Magnetic phenomena are universal in nature. The word magnet is derived from the name of an island in Greece called Magnesia, where the magnetic ore deposits were found as early as 600 BC. We are moving to the properties and classification of magnet. When a magnet is dipped in iron filings, we can observe that the iron filings cling to the end of the magnet as the attraction is maximum at the ends of the magnet. These ends are known as the poles of the magnets. Magnetic poles always exist in pairs. Whenever a magnet is suspended freely in mid-air, it always points towards the north-south direction. Pole pointing towards geographic north is known as the north pole, and the pole pointing towards geographic south is known as the south pole. In case of magnet, like poles repel, while unlike poles attract. We are moving to the types of magnet. We may have 3 different types of magnets, like permanent magnet, temporary magnet, and electromagnet. Permanent magnets are those magnets that are commonly used. They are known as permanent magnets because they don't lose their magnetic property once they are magnetized. There are 4 types of permanent magnets: ceramic or ferrite, alnico, samarium cobalt, and neodymium iron boron. Temporary magnets can be magnetized in the presence of a magnetic field. When the magnetic field is removed, these materials lose their magnetic property. Iron nails and paper clips are examples of temporary magnet. Electromagnets consist of a coil of wire wrapped around the metal core made from iron. When this material is exposed to an electric current, a magnetic field is generated, making the material behaving like a magnet. The strength of the magnetic field can be controlled by controlling the electric current. We are moving to the origin of magnetism. When most people think of magnetism, they think about the magnetic force experienced between two magnets. The magnetic force is caused by the magnet's magnetic field and points in the direction of the field lines. If you have two magnets next to each other, their north poles are facing each other or their south poles are facing each other, you can see that the field lines move away from each other, so you feel a repelling force between the two magnets. If you put the north pole of one magnet next to the south pole of the other magnet, then the field lines go straight from the north pole of the first magnet to the south pole of the second, and you feel an attractive force between the two magnets. This is why opposite pole attracts and like poles repel. The origin of magnetic properties in a substance is because of 2 types of motions of electrons: orbital motion around the nucleus and spin motion around its own axis. An electron in an atom behaves like a tiny magnet. Electron, being charged particle and undergoing these motions, can be considered as a small loop of current which possesses a magnetic moment. Each electron thus has a permanent spin and an orbital magnetic moment associated with it. Magnitude of magnetic moment is very small and is measured in the unit of Bohr magneton. We are moving to the basic parameters for magnetic materials. Magnetic field. The region around the magnet where its magnetic influence can be experienced is called a magnetic field. The direction and strength of a magnetic field are represented by magnetic field lines. The magnetic field lines are formed due to various reasons like orbital movement of electrons, current flowing in a conductor, etc. Magnetic field lines result in the formation of continuous or running closed loops. The tangent to the field line at a given point indicates the direction of the total magnetic field at that point. The greater the number of field lines crossing per unit area, the higher the intensity and stronger the magnitude of magnetic field. There is no intersection between magnetic field lines. The magnetic field lines by convention enter through the south pole and comes out of the north pole. The magnetic field lines are stronger near the poles of the magnet.
Place the bar magnet at the center of the sheet and slowly pour iron fillings over it. Tap the sheet like this 2-3 times. If we look at the fillings closely, a formed pattern can be seen. This pattern shows the force exerted by the magnet on the iron fillings. The field in which the force is exerted is called the magnetic field. The lines on which the fillings can be seen are known as magnetic field lines. If we carefully observe the iron fillings, then we will find that at one place they are collected very closely and at other places very less. The collection of iron fillings represents the strength or weakness of magnetic field lines. According to the convention, the direction of field lines is taken from the north to south. Inside the magnet, it is taken from south to north.
Magnetic intensity is defined as the magnetic field strength produced by a magnet or electric current. It quantifies the magnetizing force regardless of the medium in which the field exists. The SI unit for magnetic intensity is ampere per meter. Magnetic flux is defined as number of magnetic field lines passing through a given closed surface. It provides the measurement of the total magnetic field that passes through a given surface area. Magnetic flux density is defined as the force acting per unit current per unit length on a wire placed at right angles to the magnetic field. It is a vector quantity. Magnetic flux is given by B equal to F by IL, where L is the wire's length, F is total force acting, and I is the current flowing. When a substance is placed in a magnetic field H, then the density of the magnetic field lines that pass through the substance per square meter is known as magnetic flux density. It is given by B equal to mu naught H, where mu naught is called the permeability and is defined as the degree to which a substance gets magnetized. Motion of electrons in atoms give rise to phenomenon called magnetism. Basically, two types of motions are associated with the electrons: motion of the electrons in an orbit within the nucleus and spin of electrons around its axis. The spin and orbital moments impart magnetic moment on each electron, forcing them to behave as tiny magnets. The rotational force experienced by a magnet when placed in a magnetic field perpendicular to its magnetic axis is defined as the magnetic moment of the magnet. Magnetization in case of a magnetic material can be defined as the total magnetic moment per unit volume. Magnetic susceptibility is a dimensionless quantity that indicates how much a material will become magnetized in response to an external magnetic field. It quantifies the degree of magnetization of a material when it is subjected to a magnetic field and helps to classify materials based on their magnetic properties. Ratio of intensity of magnetization produced in a sample to the magnetic field intensity which produces the magnetization is defined as magnetic susceptibility. Magnetic permeability is defined as the ratio of magnetic induction to the magnetic intensity. It is a scalar quantity and is denoted by the symbol mu. Magnetic permeability helps us to measure a material's resistance to the magnetic field or measure the degree to which the magnetic field can penetrate through a material. If the material has greater magnetic permeability, the greater will be the conductivity for magnetic lines. Permeability also depends on several factors such as the nature of the material, humidity, position in the medium, temperature, frequency of the applied force, etc. If the material has greater magnetic permeability, the greater will be the conductivity for magnetic lines of force. Permeability also depends on several factors such as nature of the material, humidity, position in the medium, temperature and frequency of the applied force. Magnetic permeability is always positive and can vary with a magnetic field. The magnetic permeability is given by the formula mu equal to B by H, where B is magnetic flux density and H is magnetizing field. The SI unit for magnetic permeability is Henry per meter. There are different types of permeability. Permeability of free space. It is the ratio of magnetic intensity in vacuum and magnetizing field. The permeability of free space, also known as the permeability of air or vacuum. It is represented as mu naught is equal to B naught by H. Permeability in a medium. It is the ratio of magnetic intensity in the medium to the magnetizing field. That is, mu is equal to B by H. Relative permeability is a dimensionless quantity. It is the ratio of two quantities with the same unit. So, relative permeability has no unit. It is the ratio of permeability in free space to the permeability in medium. Dear learners, let us go through a small quiz. Hope you have enjoyed the quiz. Let us move to the next section of this topic. Now we'll discuss different types of magnetic materials. There are basically 5 types of magnetic materials. Diamagnetic material. The main constituent part in every material is the atom. An atom has electrons which are continuously rotating around the positively charged nuclei. Due to this motion of the electron around the nuclei, a magnetic field is generated, and this property of the material is known as diamagnetism. The magnetic field developed is so weak that it doesn't exhibit its effect externally. All the materials in the universe are diamagnetic in nature. When an external magnetic field is applied to a material, the orbital motion of the electrons changes and a small induced magnetic moment establishes, which is opposite to the direction of the external magnetic field. Under the influence of strong external magnetic field, diamagnetic material attracts towards the area where magnetic field is weak. It is such a weak property of the material that it doesn't affect everyday life. Diamagnetism was discovered and named in 1845 by Michael Faraday, who demonstrated that all the materials exhibit diamagnetism and it is a property of matter. In diamagnetic materials, there are no permanent atomic dipoles due to the pairing of electrons. When an external magnetic field is applied, dipoles are induced in the diamagnetic material in such a way that induced dipoles oppose the external magnetic field according to Lenz's law. Thus, all the materials whose atoms contain paired electrons show diamagnetic properties. Some of the most common examples of diamagnetic materials are copper, zinc, bismuth, silver, gold, antimony, marble, water, glass, etc. There are no atomic dipoles in case of diamagnetic materials because the resultant magnetic moment of each atom is zero due to paired electrons. Let us move to the properties of diamagnetic material. There are no atomic dipoles in the diamagnetic materials because the resultant magnetic moment of each atom is zero due to paired electrons. Diamagnetic materials are repelled by a magnet. The substances are weakly repelled by the field. So, in a non-uniform field, these substances have a tendency to move from a strong to a weak part of an external magnetic field. The intensity of magnetization is very small, negative, and proportional to the magnetizing field. Magnetic susceptibility is small and negative. The relative permeability is slightly less than unity. Diamagnetic materials are independent of temperature. These materials do not obey Curie's law. A rod of diamagnetic material comes to rest with its length perpendicular to the direction of the field when it is suspended in a uniform magnetic field because the field is strongest at the poles. A diamagnetic liquid in a U-tube depresses the limb, which is between the poles of a magnet. The magnetic dipole moment is very small and opposite to the magnetic field. The magnetic dipole moment is very small and it is opposite to the magnetizing field. If a liquid is placed on a watch glass placed over two pole pieces that are sufficiently apart, then liquid accumulates in the middle where the field is weakest. The origin of diamagnetism is the induced dipole moment due to change in the orbital motion of electrons in an atom by the applied field. Let us move to the next type of magnetic material, that is paramagnetic material. Paramagnetism is the magnetic state of an atom with one or even more unpaired electrons. In a paramagnet, magnetic moments tend to be randomly oriented due to thermal fluctuations when no magnetic field exists. In an applied magnetic field, these moments start to align parallel to the applied field such that the magnetization of the material is proportional to the applied field. Paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. They have the tendency to move from a region of weak magnetic field to a strong magnetic field. That is, they get weakly attracted to a magnet. The individual atoms of a paramagnetic material possess a permanent magnetic dipole moment of their own. On account of this ceaseless random thermal motion of the atoms, no net magnetization is observed. In the presence of an external field which is strong enough and at low temperatures, the individual atomic dipole moment can be made to align and point in the same direction as the magnetizing field, and thus magnetization increases. Paramagnetic materials have some unpaired electrons, and due to these unpaired electrons, the net magnetic moment of all electrons in an atom is not added up to 0. Hence, an atomic dipole exists in this case. On applying an external magnetic field, the atomic dipole aligns in the direction of the applied external magnetic field. In this way, paramagnetic materials are feebly magnetized in the direction of the magnetizing field. Some examples of paramagnetic materials include iron oxide, oxygen, magnesium, molybdenum, titanium, lithium, etc. Let us move to the properties of paramagnetic materials. When the net atomic dipole moment of an atom is not 0, the atoms of paramagnetic substances have permanent dipole moment due to unpaired spin. The substances are weakly attracted by the magnetic field. In the non-uniform external magnetic field, paramagnetic substances move from a weak field region to the strong field region. A paramagnetic rod sets itself parallel to the field because the field is strongest near the pole. Paramagnetic substances obey Curie's law, according to which magnetic susceptibility is inversely proportional to its absolute temperature. The magnetic dipole moment of paramagnetic substance is small and parallel to the magnetizing field. Let us move to the next type of magnetic material, that is ferromagnetic material. Ferromagnetism is a unique magnetic behavior that is exhibited by certain materials such as iron, cobalt, alloys, etc. It is a phenomenon where these materials attain permanent magnetism or they acquire attractive powers. It is also described as a process where some electrically uncharged materials attract each other strongly. Ferromagnetism is a property that considers not only the chemical makeup of a material but also takes into account the microstructure and the crystalline structure. In a ferromagnetic material, in the unmagnetized state, atomic dipoles in small regions called domains are aligned in the same direction. The domains exhibit a net magnetic moment even in the absence of an external magnetizing field. However, the magnetic moments of the neighboring domains are oriented in the opposite directions. They cancel out and therefore the net magnetic moment of the material is 0. On applying an external magnetic field, these domains align themselves in the direction of the applied field. In this way, the material is strongly magnetized in the direction parallel to the magnetizing field. Let us move to the properties of ferromagnetic material. The atoms of ferromagnetic substances have permanent dipole moments present in domains. Atomic dipoles in ferromagnetic substances are oriented in the same direction as the external magnetic field. The magnetic dipole moment is large and is in the direction of the applied magnetic field. The intensity of magnetization is very large and positive and varies linearly with the magnetizing field. The magnetic susceptibility is very large and positive. The magnetic flux density of a material will be very large and positive. In case of ferromagnetic material, the relative permeability is also very large and varies linearly with magnetizing field. Ferromagnetic substances are strongly attracted by the field, so in a non-uniform field, they tend to stick at the poles where the field is strongest. Let us move to the next type of magnetic material, that is antiferromagnetic material. Antiferromagnetic material shows a behavior which is said to be antiferromagnetism. This phenomenon of magnetic moment coupling between adjacent atoms or ions occurs in materials other than those that are ferromagnetic. In one such group, this coupling results in an antiparallel alignment. The alignment of the spin moments of the neighboring atoms or the ions is exactly opposite directions is termed as antiferromagnetism. Antiferromagnetism is a phenomena in which, in case of the neighboring atoms or ions, they have similar and opposite magnetic moments. Manganese oxide is one material that displays this behavior. Manganese oxide is a ceramic material that is ionic in character, having both manganese and oxygen ions. No net magnetic moment is associated with the oxygen ions because there is a total cancellation of both spin and orbital magnetic moments. However, the manganese ions possess a net magnetic moment that is predominantly of spin origin. These manganese ions are arrayed in the crystal structure such that the moments of the adjacent ions are antiparallel. Obviously, the opposing magnetic moments cancel one another, and as a consequence, the solid as a whole possesses no net magnetic moment. We are moving to the next type of magnetic material, that is ferrimagnetic material. Some ceramics also exhibit a permanent magnetization termed as ferrimagnetism. The macroscopic magnetic characteristics of ferromagnets and ferrimagnets are similar. The distinction lies in the source of the net magnetic moments. The principles of ferrimagnetism are illustrated with the cubic ferrites. These ionic materials may be represented by this chemical formula, in which M represents any one of the several metallic elements. The prototype ferrite is Fe3O4, the mineral magnetite, sometimes called lodestone. Here, a net spin magnetic moment exists for each Fe2 plus and Fe3 plus ions, which corresponds to 4 and 5 Bohr magnetons respectively. In case of ferrimagnetic materials, a net magnetic moment arises due to the incomplete cancellation of spin magnetic moments of nearby atoms. Let us move to the applications of different types of magnetic materials. So these are the applications. Dear learners, let us go through another quiz. Hope you have enjoyed the quiz. So if we want to summarize, so in this session we have learned about different types of magnetic parameters and different types of magnetic materials. Hope you have enjoyed this session. Thank you.